Hi, everybody. It's Professor Mitchell. Today we're going to actually start Math 4B, Calc 2, by looking at Chapter 7, which is on transcendental functions. In the first section, we're looking at inverse functions and their derivatives. So we will be using this concept throughout this chapter. And what you're going to find in this section is a lot of pre-calc review, going all the way back even to Math C, which is intermediate algebra. All right, so let's get into it. One-to-one functions. You've heard of one-to-one functions before in your algebra and pre-calc courses. We don't always define them exactly like this in pre-calc. So I'm going to read you this definition, and then I'm going to do my best to say it in something closer to everyday English. So a function f of x is one-to-one on a domain D if f of x1 does not equal f of x2 whenever x1 does not equal x2 in D. So in something closer to everyday English, what this says is that a function is one-to-one if two different x's always give you two different y values. So here are a couple of pictures. In these top two pictures, you see two examples of functions that are one-to-one. So notice that if you were to pick two different x values on this graph, you would get two different y values. So for example, this x value right here would give you a y value that's down here, while an x value over here would give you a y value up here. Notice also that no matter where you draw a horizontal line through this graph, it only intersects the graph once. So that's going to give us the so-called horizontal line test, which we'll look at on the next slide. Same thing over here, the graph of y equals the square root of x. No matter where you draw a horizontal line, it only intersects the graph once. Two different x values always give you two different y values. Here are a couple of examples of functions that are not one-to-one. They are perfectly good functions, but they are not one-to-one functions. Take y equals x squared, for example. -1 and 1 are definitely two different x values. However, they give you the same y value of 1. So that function is not one-to-one. Same thing for y equals sine x. The sine of pi over 6 and the sine of 5 pi over 6 are both 1/2. So this is not a one-to-one function. Notice that the horizontal line passing through that graph intersects each graph twice. So that also makes it not a one-to-one function. All right, and that is the horizontal line test for one-to-one functions. A function y equals f of x is one-to-one if and only if its graph intersects each horizontal line at most once. All right, so now we come to our first example. Determine from its graph if the function is one-to-one. This is what's called a piecewise defined function. You've seen these before. F of x is equal to 2 minus x squared for x less than or equal to 1, but equals x squared for x greater than 1. So I am going to switch over to my tablet. Let's see, it's been a little while since I've done this. Here we go. New share. Okay. Let's see. Okay, please stand by. I'm going to pause you for just a second. Okay, here we go. Got it to work finally. Okay, so let me remind you what this function was. We're trying to determine whether it is one-to-one. The function was f of x equals 2 minus x squared for x less than or equal to 1, x squared for x greater than 1. All right, so I have a certain way that I show my Math C and my pre-calc students how to graph piecewise functions. I'm going to try with you to not explain it in quite that much detail. So hopefully you know that y equals 2 minus x squared is just an upside down parabola with its vertex at 0, 2. Okay. And so that's going to do something like this. And it's just going to continue down this way. All right, and that rule applies all the way up to x is less than or equal to 1, which is going to put us right here. And then I'm going to stop that parabola right there because that's where so-called rule number 2 kicks in. For x greater than 1, f of x is equal to x squared. So it's going to start at that same point, at the point 1, 1, and then it's going to go up in this direction. All right. So is this function 1-to-1? Well, the answer is no, because, for example, if I draw a horizontal line right here, it intersects the graph in not only 1, but 1, 2, 3 places. So this is a perfectly good function. However, it is not a 1-to-1 function. All right. So going back to presentation. All right, let's continue. On to inverse functions. Suppose that f is a 1-to-1 function on a domain D with range R. The inverse function f inverse, and hopefully you understand by now that this notation right here is not read f to the -1 power or anything like that. It's kind of unfortunate that we use this notation because it does look like an exponent. Nothing I can do about that. Anyway, that inverse function f inverse is defined by f inverse of b is equal to a if f of a is equal to b. So note that the domain of f inverse is R and the range of f inverse is D. So basically the relationship between a function and its inverse is that the x values and the y values just switch places. So that's why the domain of one function becomes the range of the inverse, the range of the original function becomes the domain of the inverse. All the x's and the y's just trade places. All right, a little bit about finding inverses graphically. I know that this is kind of hard to see, and I'm sorry to say, when I'm standing in front of a class, I know how to zoom in on this. Anyway, hopefully you can see it okay. All right, not going to spend a lot of time on this. So to find the value of f at x, we start at x, go up to the curve, and then over to the y-axis. So that's just your most basic, how do you find the value of a function from the graph, all right? I think we covered that in beginning algebra. The graph of f inverse is the graph of f, but with x and y interchanged. To find the x that gave y, we start at y, go over to the curve, and then down to the x-axis. Notice that if you're dealing with a one-to-one function, you're only going to get one single x value out of that. And again, the domain of f inverse is the range of f. The range of f inverse is the domain of f. All right, to draw the graph of f inverse in the more usual way, and hopefully you have some memory of this from pre-calc, we reflect, it says the system, I would call this just the graph, across the line y equals x. So here is your original graph. Here's the line y equals x. So if you reflect this graph across the line y equals x, you get this graph here. So when I'm standing in front of a class, what I like to do is actually take a piece of paper, draw the graph of f in some nice wet marker, and then I fold the paper over, and where the smear comes up is the graph of the inverse function. Okay, and then interchange the letters x and y. We now have a normal looking graph of f inverse as a function of x. All right, now a little bit of review of finding inverses algebraically, and I do have an example of this. Solve the equation y equals f of x for x. This gives a formula x equals f inverse of y, where x is expressed as a function of y. Once you have that, you interchange x and y, which would give you the formula y equals f inverse of x, where f inverse is expressed in the conventional format with x as the independent variable and y as the dependent variable. All right, so here is our next example. We're going to find f inverse of x and identify the domain and range of f inverse. And then as a check, we'll show that f of f inverse of x is just x, and f inverse of f of x is just x. Okay. So pausing this while I bring up the tablet. All right, here we go. So one of the questions that we're going to be, that they asked, it wasn't, I don't think, their first question. They wanted to know what are the domain and the range of f inverse. So I was thinking if we identify the domain and range of f, that will answer that question, because then we can just switch. The domain of f will become the range of f inverse. The range of f will become the domain of f inverse. So notice that the domain of f is x greater than or equal to 5, aka interval from 5 to infinity, including the 5. And you see why that is, right? In order to get a real number out of this function, x minus 5 has to be at least 0. It can't be negative. The range of f, well, what kind of number can you get out of a square root? You can get any number that's greater than or equal to 0. All right, and that won't change when you multiply that number by 4. So the range of f is the interval from 0 to infinity, including 0. And so now we have already answered one of the later parts of the question. This interval is going to be the range of f inverse. We don't even have f inverse yet, but we already know its range. And we know that this is the domain of f, and that's going to be kind of important when you f inverse, when you see what f inverse actually looks like. Okay, so let's do that. Let's find f inverse now. All right, so it said the first step was to solve this equation for x. So the first thing I'm going to do is replace this f of x with a y. And now I'm going to work on solving this for x. So the first thing I'll do is divide both sides by 4. And that gives me y over 4 equals the square root of x minus 5. Now I'm going to square both sides. And that's going to give me y over 4 squared equals x minus 5. And then finally add 5 to both sides and you get x equals y over 4 squared plus 5. All right, so we have x written as a function of y. Now remember, in the original function, y had to be at least 0. All right, you can't get negative numbers out of a square root. So it's worth pointing out here that y is greater than or equal to 0. And now when I interchange x and y, which is the second step of finding the inverse function, and maybe I'll do this in blue, you get y equals x over 4 squared plus 5, where x is greater than or equal to 0, which goes along with, remember this? We found earlier that the domain of f inverse is the interval from 0 to infinity, all right? And that would be easy to miss because look, y equals x over 4 squared plus 5. That's just an ordinary old quadratic function. The natural domain of that function is all real numbers. So when we write down the inverse of this function, we are definitely going to have to attach a note that says that this function has a restricted domain. The domain is restricted to x is greater than or equal to 0. Okay, isn't that fun? All right, what else did they ask me to do? They wanted me to confirm that this answer is correct by checking f inverse of f of x and also f of f inverse of x. All right, so let's just recap what we have. So the original function was f of x equals 4 times the square root of x minus 5. And we think that the inverse function is f inverse of x equals x over 4 squared plus 5 for x greater than or equal to 0. Okay, so now we're going to check, and it really doesn't matter what order you do this. Why don't we do f inverse of f of x? So a little bit of function composition. My Math C students just love function composition. Just kidding, they don't like it all that much. They find it confusing, which it kind of is at first. All right, so f inverse of f of x. What is f of x? It's 4 times the square root of x minus 5. And then what does function f inverse do? It takes a number, divides that number by 4, squares the answer, and then adds 5 for x greater than 0, which may or may not be important. It's going to be important in one or the other of these. Okay. So when you replace that x with 4 times the square root of x minus 5, this is what you get. And we're going to cancel the 4s. And that's going to leave me with the square root of x minus 5 squared plus 5. And guess what? The square root of x minus 5 squared is just x minus 5. And of course, when you add 5 to x minus 5, what do you get? You get x. Woohoo! All right, that is exactly what we were hoping for. If we had gotten anything else other than x, it would have meant something's wrong, okay? With inverse functions, f inverse of f of x and f of f inverse of x are always, always, always supposed to come out to just be x. Something you learned in pre-calc. All right, now let's go the other way. What did we just do? I already forgot. Okay, now let's do f of f inverse of x. So f inverse of x, and remembering that it did have a domain restriction, is x over 4 squared plus 5. And what does function f do? It takes a number, subtracts 5, takes the square root, and then multiplies the answer by 4. Okay, so let's stick x over 4 squared plus 5 in here. So the first thing that's going to happen there is that the 5s are going to drop out. That's going to leave me 4 times the square root of x over 4 squared. Now, this part's very exciting. This is where our domain restriction comes in handy. All right. Here's something that was hopefully drilled into your head in Calc 1. Okay, just a little aside. I'm going to put it up in this top corner. What is the square root of x squared? What is the square root of x squared? If you said x, well, then you weren't totally paying attention in Calc 1. All right. If I don't know anything about x, the best I can say about the square root of x squared is that it is the absolute value of x. Okay. So why don't we say that about this, that the square root of x over 4 squared is just the absolute value of x over 4. But guess what? Remember that domain restriction? We know that x is greater than or equal to 0. So we can actually say that the absolute value of x over 4 is just x over 4. And again, that's because x is greater than or equal to 0. And that's how we get our x that we're supposed to get. Woohoo! All right, so everything checks out with that example. All right, so back to the presentation. All right, so what you're looking at here are just the graphs of f and f inverse from the last example. This is the graph of f of x equals 4 times the square root of x minus 5. And up here we have the graph of f inverse of x equals x over 4 squared plus 5. All right, so this is a calculus class, and so far we haven't done a stitch of calculus, so let's change that. And let's talk about derivatives of inverses of differentiable functions. So I've added a little something to the picture that you were just looking at. I have added some tangent lines. So now we're looking at the graphs of f and f inverse with the lines tangent to the graph of f at x equals 6. That's this line right here. And also tangent to the graph of f inverse at x equals 4. That's this line here. So looking at this line and this line, can you tell what is the relationship between the slopes of those two lines? And let's see if I can give you a little hint. Okay, I was having a little trouble getting my bearings there, so I thought I would add a couple of points. All right. So again, the question was, what is the relationship between the slopes of these two tangent lines? So as a hint, let me just point out that if you started from this point and traveled to this point using rise over run, it looks like you would rise, oh boy. Okay, usually I do this as a dotted line. I think I'll give up on that idea. So we're gonna rise 6 and then run 2. So rise 6, run 2. And then to get from this point to this point, we're going to rise 2 and then run. I'm sorry, let me try that again. It's rise 4. Yeah, rise 4, run 2. And then here, this is rise 2, run 4. All right. So the answer to the question, what is the relationship between the slopes of those two tangent lines? They are reciprocals. All right. So that is, if I was going to summarize this whole section in one little sentence, it would be that. All right. So let's look at this theorem. This theorem looks very intimidating when you look at it like this, but it basically says exactly what we just said. All right. And I will say that for you again after I read the theorem. So this is called Theorem 1, the derivative rule for inverses. If f has an interval I as domain, and f prime of x exists and is never 0 on the interval I, then f inverse is differentiable at every point in its domain, which remember is the range of f. The value of the derivative of f inverse at a point B in the domain of f inverse is the reciprocal of the value of f prime at the point A, which is f inverse of B. So in other words, the derivative of f inverse of B is equal to 1 over f prime. And I don't like when they write it like this. So if you're taking notes, why don't you write down 1 over f prime of A? So you just have to remember, let me get my pen here. You just have to remember that f of A is equal to B. All right, so instead of writing f prime of f inverse of B, why don't we say f prime of A here? I think that makes it a little less scary. All right. So I don't know if your Calc 1 instructor talked about this, but calculus was independently discovered by two different mathematicians who were working separately. One of them was Isaac Newton, and the other one was a German mathematician named Leibniz. This notation here is the notation that Newton used. This is Leibniz notation. So they've written it both ways. So you can either write it like that, or you can say the derivative of f inverse with respect to x at the point x equals b is equal to 1 over the derivative of f with respect to x at, and again here I would say at x equals a. I think that makes that a little simpler. All right, again, I will admit it looks kind of confusing and scary at first, but it's actually a pretty simple concept. Just think about this picture. This is how I always think about it. All right, so we are on to our last couple of examples. All right, so in the first example, given f of x equals 2x squared for x greater than or equal to 0, we need this domain restriction to make this function 1-to-1 at the point a equals 5. So the first thing we'll do is find f inverse of x. Then we'll graph f and f inverse together. And then finally, we will evaluate the derivative of f with respect to x at x equals a, and the derivative of f inverse with respect to x at x equals f of a, to show that those two derivatives are reciprocals of each other. Okay. All right, so let me switch over to the tablet. Okay, so the first thing they asked me to do, f of x equals 2x squared, x greater than or equal to 0. They want us to find f inverse of x, so that's pretty easy. Let's put a y here instead of f of x. And then we're going to solve for x. So first divide both sides by 2. Y over 2 equals x squared. And then technically we're using the square root property. Remember that x is greater than or equal to 0. Okay, so because x is greater than or equal to 0, I actually don't have to use the full square root property. If I didn't know that x was greater than or equal to 0, I would have to say that x is either the positive or negative square root of y over 2. But because we know that x is greater than or equal to 0, I can just do this. And I get that x is equal to the square root of y over 2. All right, so now we'll switch x and y. We get y equals the square root of x over 2, which means f inverse of x is the square root of x over 2. All right. And then I think they wanted to know what is the derivative of f at x equals 5. So the derivative of f with respect to x at x equals 5, that would be the derivative of 2x squared with respect to x at x equals 5. All right, so if there's one thing you remember from Calc 1, I hope, or maybe a handful of things, I hope one of them is how to differentiate a function like 2x squared. All right, that would be 4x, right? And then when you plug in x equals 5, you get 20. All right, so the derivative of f with respect to x at x equals 5 is 20. So now, let's see, what is f of 5? F of 5 is 2 times 5 squared, which comes out to 50. So when we're comparing the derivative of one function and the derivative of the inverse, when we look at the derivative of the inverse, we're going to be looking at that derivative at x equals 50. Okay. All right, so the inverse function is the square root of x over 2. So now I'm just thinking about what is the best way. Well, we're in Calc 2, right? Let's use the chain rule. Okay, so let me go over to the next page. I'm going to rewrite that function as x over 2 to the power 1/2. And we're differentiating that function at x equals 50. So the derivative of x over 2 to the power 1/2 would, by the chain rule, would be 1/2 times x over 2 to the power -1/2 times the derivative of x over 2, right? And the derivative of x over 2 is 1/2, isn't it? All right, so what does that come out to? We have 1/4 times x over 2 to the -1/2. Okay, I'm kind of, sometimes I do go overboard with showing my work. So why don't we plug in our 50 now? So we have 1/4 times 25 to the -1/2. 25 to the -1/2 is 1 over the square root of 25, which comes out to 1/4 times 1/5, which is 1 over 20. Woohoo! We were looking for that to come out to be the reciprocal of what we got there. So I'm pretty sure that was all they wanted us to do. So notice that we actually didn't use that inverse function theorem. The purpose of this example was to kind of confirm the inverse function theorem with one example. So now let's go back to the slide. I think in the next, which is also the last example, and come to think of it, I'm not sure why I had this grid here. I never used it. Oh, well. All right, example 2. Let f of x equal x squared minus 4x minus 5 for x greater than 2. We want to find the value of the derivative of f inverse at, with respect to x at the point x equals 0, which happens to be f of 5, okay? So the great thing about the inverse function theorem is that it allows you to find the derivative of an inverse function without actually finding the inverse function. All right. I think that if I sat all of you down and had you calculate the inverse of this function, you would eventually be able to do it. You might be a little rusty on how to do it at first. You'd have to do some fun stuff like complete the square and this and that. But the point is, you don't have to do any of that. Okay, so let me show you how this works. I'm going to switch over to my tablet, and then we will be done with this section. All right, so in this example, we are looking for the derivative of f inverse with respect to x at x equals 0, which they happen to mention was f of 5. So according to the inverse function theorem, that's going to be the reciprocal of the derivative of f with respect to x at x equals 5. Okay, that makes it nice and easy. All right, and of course, the derivative of f with respect to x is 2x minus 4. So I should put parentheses here. All right, and when I put 5 into 2x minus 4, I get 6, right? So it looks like the derivative of this inverse function at x equals 0 is 1/6. And that's it. We were able to calculate that derivative without finding the inverse of function f. All right, so that's going to take care of section 7.1. We'll see you next time for 7.2.